Today we're going to move on a little bit further here, guys. Stuff that we've done already with friction and forces and whatever, that's not done. We're still not done with that, but we're going to go a little bit deeper so that we're able to analyze slightly more complicated problems involving those forces like friction and applied force and normal force and other forces. We talked very briefly the other day about what a free body diagram was. Sometimes we call it an FBD. Free body diagram we learned the other day shows all forces acting on an object. The normal force, the force of gravity, the force of friction, whatever force, the force of air resistance, whatever force happens to be acting on an object, we have to include it in our free body diagram. Now, when we do that diagram the other day as an example, we saw that there were other forces, there were other variables that we sometimes included with that free body diagram, like the mass of the object, like the acceleration and so on. Those things aren't technically required for the free body diagram. We just sometimes put them in there because it's convenient. Okay, what's needed, what's required for a free body diagram? All of the forces acting upon an object. For example, that was like the world's shortest set of notes, wasn't it, right there? For example, 3.1 on 131 says, a car with weight Fg, and we know that what weight is, right? Weight is the force of gravity acting on an object. So the weight of the object, the force of gravity acting on the object, the car, is 10,000 newtons downward, and it's coasting on a level road. The car experiences a normal force of, well, 10,000 newtons up. We could have predicted that, right? The force of gravity is usually the same as the normal force. For us, it has been every single time so far. There's a force of air resistance of 2,500 newtons backwards and a force of friction exerted by the road on the tires of 500 newtons backwards. We want to draw a free body diagram for this situation. Here's the road. Here's the car. I don't need to draw wheels on the car or fancy decals on the car or somebody waving out the window or fancy shape or anything like that. It doesn't matter. You draw it easy. Okay? If you're not a very good artist, then just draw a box. That car has a force of gravity acting down, a weight, a force of gravity acting down of 10,000 newtons. It also has a normal force acting up of 10,000 newtons. I want to draw that normal force acting up the same length as I draw the force of gravity because it's the same value. We want to draw these vectors more or less to scale if we can. We know both values here are the same, so we should draw both vectors approximately the same length. It's going to be 10,000 newtons as well. Now, that's not the only place I could have drawn that. I could have drawn the normal force right here. I could have drawn it over here. It doesn't matter as long as it shows the magnitude and it shows the direction. So don't lose any sleep over the actual placement of it. If you've got 10,000 newtons acting on this object, wherever you draw it on this object, doesn't matter as long as it's going in the right direction. What else we got? Well, let's assume that this car is moving to the right. If the car is moving to the right, then we're going to have a force of air resistance acting to the left. And it's going to have a value of 2,500 newtons. Why did I draw that quite a bit shorter than I drew the 10,000 newton normal force and force of gravity? Yeah, it's a lot smaller. The force of gravity and normal force are a lot bigger than the force of air resistance, so the vector should be drawn a lot longer. Now, we also have a force of the road on the tires. It says it's also backwards. It's 500 newtons. So we're going to draw that one really short here to indicate that it's even smaller than the force of air resistance backwards. Let's call that FF. 500 newtons. Is there anything else that I should draw on this free body diagram? Yeah? No. No, there's nothing. We're not told about any more forces that act on it. If there are more forces that act on it, we certainly don't know anything about them. So there's nothing else for us to draw. Nothing else for us to label. 4 forces, force of air resistance, the force of friction, normal force, and the force of gravity. Now, the nice thing about this question, and about a lot of questions, is that we can actually get rid of a couple of forces. We want to draw them. It's important that we should draw them. But we can cross a couple of them off here. Which ones do you think we can cross off? Which ones do you think that we can cross off there, Jace? Which ones do you think we can cross off? Yeah. Why do you think we can cross off the normal force and gravity? They balance out, yeah. So the net force upwards and downwards ends up being equal to 0. That means in the end here, in this problem, we don't need to analyze the up and down motion because there's balanced forces. We need to analyze the forces that aren't balanced. In other words, we need to analyze the force of friction and the force of air resistance here. All right? I want you to take a look at these two questions on page 131, please. All you're asked to do is draw free body diagrams, okay? That's the first step in actually mathematically analyzing these problems. So we want to make sure that you're good with that before we move on to the math problems, okay? Give you about 3 or 4 minutes to see what you can do here. All right, let's take a look here. Question number 1. We're going to do both of these just to make sure that you're good here, since you can't really see the answers there. Driver in example 3.1 sees a pedestrian and steps on the brakes. The force of air resistance is 2,500 newtons backwards. With the brakes engaged, the force of friction is 5,000 backwards. Draw a free body diagram for that situation. Now, once again, here's the car. We had a force of 10,000 newtons acting downwards. That's the force of gravity. And we also had the normal force acting upwards of 10,000 newtons. We draw those in even though it doesn't mention them specifically in this question because they're there. So we should draw them in. They cancel each other out, but they're still there. Now there is that force of air resistance that acts backwards. We're going to draw it about like this. Okay, we're going to actually let's make these ones longer here. Okay. Draw that force of air resistance backwards. It's going to be 2,500 newtons. And now we have a force of friction that's not 50 newtons, or I think it was 50 newtons in the last question. Now it's 5,000 newtons because the brake is being applied. We should draw that one about twice as long as the force of air resistance, and we should draw it about half as long as the normal force and the force of gravity. So let's label that the force of friction now is 5,000 newtons. Once again in this question, normal force and gravity would cancel, but we're still going to draw them in there because they're there. Let's take a look at the second one now. It says a car moving at a constant speed, constant velocity starts to speed up. The weight of the car is 12,000 newtons down. The force of air resistance is 3,600 newtons. With the engine engaged, the force of friction exerted by the road on the tires is 7,200 newtons forward. Hey, how is that one possible? We got air resistance going backwards. That means the car is going forward, right? How can we have a force of friction going forward if the car is going forward? Anybody explain that one to me? Seems like maybe there's a typo here on this. Rucker? Yeah. Without friction, not only would your car not stop when it's moving, but without friction, your car wouldn't start when it's at rest. It's friction between the tires and the road that propels it forward. Static friction between the tires and the road that propels it forward. So it's absolutely possible to have friction that's helpful, and in this case it is, right? It's pushing the car forward. So let's draw this one now. Once again, we've got this car, but this time the weight of the car is 12,000 newtons. We'll call that Fg, 12,000 newtons. We have a force of air resistance of 3,600 backwards. It's going to be drawn about like this, maybe a little bit longer. Let's draw the force of friction between the road and the tires. It's propelling it forward, 7,200 newtons, like this. Hey, did anybody draw that 7,200 newtons, by the way, over here? Would that be okay to draw it over there? Of course it would. It doesn't matter where you draw it as long as you draw it the right length, approximately the right length at least, and in the right direction. Okay, are we finished? Is that it? If we're finished here right now, what's going to happen to this car? Not only is this car going to go forward, it's also going to go through the ground. Okay? Clearly the car doesn't do that. So there must be a force that counters gravity here. And in fact, if the car is going to stay on the road horizontally, then that force must be the exact same value as gravity. It's going to go up this way. We're going to call that Fn, and its value is 12,000 newtons. We know it's the same value because presumably this car isn't going up or down. It's just going horizontally on the road. Now, what are we really going to do with these free body diagrams? What it's going to allow us to do is solve problems involving more than one force. Notice the problems we've solved so far, and there's been quite a few of them, especially on that worksheet that you had for homework last night. Quite a few force problems, but they all involve one force. We say F is equal to m times A. F is the net force, but there is only one force acting to cause the net force. Today we're going to learn to deal with more than one force. We call them multi-force problems. The first step in solving one of these multi-force problems is to draw a free body diagram. That's why we just practiced them. If we get the free body diagram wrong, then we're going to get this question wrong. It's the very first step upon which everything else is built in these multi-force problems. Once you draw it, hey, if there happens to be a couple forces that you can cancel each other out, then go ahead and do that. Like the normal force and the force of gravity. They don't always cancel, but they cancel out fairly often. So look for things that are the same in opposite directions that can cancel. Cross them off. Simplify things a little bit. Travis? Yep. 7,200. Yep. Okay. Good question. Travis's question was talking about canceling things out, and clearly we could cancel these ones out, right? They disappear because they're the exact same value. If we had a force of friction of 7,200 forward and a force of air resistance of 7,200 backwards, then they would cancel each other out as well. Now, Travis's question is, I think, can we kind of cancel this one out and then change that to 3,600? Is that right? Is that your question? Technically, the answer to that is yes. Technically, you could. But I'm going to suggest you don't. And the reason I'm going to say that is because these questions sometimes become quite complicated. And if we start doing things like that, then it sometimes adds to how complicated it is. Okay? You'd get away with it in this question, and it's not wrong even. But it's just not a habit that we necessarily want to get into. Okay? It becomes a little bit trickier to see things sometimes when we do that. So I'm going to suggest that you don't do that. Cross off things if they're the same value to simplify it, but don't fudge it like that to make it the same value. What do we do next? Well, if all the remaining forces are in one dimension, and they're not always going to be, if they're in two dimensions, we're going to learn to solve that in a week or so. Okay, if they're in one dimension, in other words, either on the x-axis or the y-axis, then what we're going to do first is write down a new equation for the net force. We said net force is equal to m times a, right? That's Newton's second law. But the net force is also equal to all of the forces added together. Remember we talked about my net salary? Okay, the net salary is all of the things added together. Okay, it's regular pay plus sick pay plus negative employment insurance plus negative Canada pension, so on and so on and so on. We add all those things up and we get my net pay. We add up all of our forces, F1 plus F2 plus FF plus F air resistance plus whatever forces act here, it adds up to give me my net force, my total force, my unbalanced force. Now, we also know that the net force, just said a minute ago, the net force is equal to m times a. So what we're normally going to do there is replace the net force with m times a. That makes ma equal to the sum of all of these forces added together. And at this point, once we're at step 2, we're done the hard part. Once we get to step 2, it's a matter of just plugging some numbers in, solving for what you're looking for. And we'll see an example of that in just a minute. Here's another problem. But this one's going to actually ask you to solve for something as opposed to just to draw a free body diagram. says two people, A and B, are dragging a canoe out of a lake onto a beach using light ropes. Each person applies a force of 60 newtons forward on the rope. The force of friction exerted by the beach on the canoe is 85 newtons backwards. Starting with the free body diagram, calculate the net force on the canoe. Let's draw that free body diagram now. Here's my canoe. There's a force of 60 newtons forward. We'll call that F1. Person 1 is pulling with 60 newtons. And person 2 is also pulling with 60 newtons forward. Now, there's a force of friction of 85 newtons backwards. So that's going to be slightly longer than F1 or F2. We'll call that FF, is 85.0 newtons. Now, there is a force of gravity acting on this canoe, and there is a normal force acting on this canoe, but we're kind of looking at it from above here. We don't know what the values of gravity or the normal force are either. No, we don't. You're right. Now, just because we don't know the values doesn't mean we can't draw the vectors. We don't know how long to draw the vectors, but in the end, if we're looking at it from above, there's not really a way to draw the vectors. Okay, if we're looking at it from above like we are in that picture there. So that's good enough. In the end, we know the normal force is going to cancel it with gravity anyways, so it's not such a big deal that we're not able to draw that normal force and gravity in this one. Okay, what's that first step? It's the first step after we have our free body diagram drawn. Well, remember we said F net is equal to the sum of the forces. In this case, it's F plus F1 plus F2. Now, normally the next step would be to replace F net with M times A. But since we're looking for the net force, I'm not going to do that this time. I'm just going to leave it F net is equal to the sum of the forces. And then I'm going to plug my numbers in. FF is 85.0 newtons. F1 is 60 newtons. F2 is 60 newtons. Would you agree with that? Is that all right, Josh? Yes, good. FF, the 85 Newton force, should be negative. Can anybody else besides Josh tell me why? Aiden? Yeah, it's going opposite direction. If F1 and F2 are positive, then FF has got to be a negative value. Now let's add up these forces here. 85 plus 60 plus 60 is going to give me 35.0 newtons. The net force acting on this canoe is 35.0 newtons. Now, if I was looking for the acceleration of the canoe, I would have plugged in that expression m times a to replace F net. But since I was just looking for the net force, I didn't need to do that. That's not a hard question, is it? They get a little bit trickier, of course. But in the end, this is the basic method that we're going to use to solve all of these problems. We just kind of build around this. Does that make sense? All right. Let's try these two questions, please. All right, let's take a look at one of these questions. Start with number one here, okay? It says two dogs, A and B, are pulling a sled across a horizontal, snowy surface. Dog A exerts a force of 200 newtons forward, while dog B exerts a force of 150 newtons forward. The force of friction exerted by the snow on the sled is 60 newtons backward, and the driver attempts to slow down the sled by pulling it back with a force of 100 newtons backwards. Starting with the free body diagram, calculate the net force on the sled. So I think this is a great question for us to start off with going over as a group here, because there's a little bit of confusion that can arise from this question, not so much from the forces that are acting, but from the objects. There's two dogs, there's a person, and there's a sled. There's four objects. How do we include all four of those objects in our free body diagram? Well, the simple answer to that is we don't need to. We're trying to find the net force on the sled. So let's draw a free body diagram of the sled. That free body diagram would show a force acting to the right. We'll call that FA for the force of dog A. of 200 newtons. We'll draw FB, the force of dog B, acting to the right as well with a force of 150 newtons. I haven't drawn the dogs. I don't care about the dogs. I don't care whether it's dogs pulling this with 150 and 200 newtons, or whether it's a tow truck pulling it, or whether it's a bunch of kids pulling it. It doesn't matter. This sled experiences those two forces forward. Don't bother trying to clutter this diagram up with drawing the dogs and drawing the person pulling it backwards and so on. A friction is going to be backwards like this with a force of 60 newtons. The driver is attempting to slow it down with a force of 100 newtons. So let's say FD, the force of the driver, 100 newtons backwards. Now, I heard somebody ask a question, and then somebody else answer this question a little bit earlier. The question was, do we need to pay attention to the normal force and the force of gravity? The answer to that person gave was no, and that's true. We don't have to pay attention to the normal force and the force of gravity. But the reason was wrong. Okay, the reason that the person gave was, well, they're not mentioned. If they're not mentioned in the question, we don't have to pay any attention to them. That's not true. If they cancel, we don't have to pay any attention to them. Now, in this case, we don't know what the mass of this sled is, so we don't know what the force of gravity is acting down. But there is one. And we know the normal force, whatever its value, will be the same value as the force of gravity. They cancel because they're the same value. So we don't pay any attention to them because they cancel, not because they're not mentioned in the question. All right, so how do we find the net force? Let's say that F net is equal to FF plus FD, right? All of the forces added up, plus FA plus FB. Let's add those up. FF is what? Well, what's the value of FF there? Good. Negative 60 newtons because it's drawn to the left. Good. Brendan, what's the value of FD? Good. It's negative 100. You can either add negative 100 newtons here, or you can just say subtract 100 newtons. It doesn't really matter at this point. We're adding forces together, but when you add a negative, it's the same thing as subtracting, right? Alex, what's the value of FA? Right, and it's positive because it's drawn to the right. And what's the value of FB? Krista, what's the value of FB? And it's positive because it's to the right as well. So now let's add these up. Neg 60 plus neg 100 plus 200 plus 150, that's going to give me, what is that, 250, 190? Is it 190? Oh, yeah. Of course it is. Gives me 190 newtons, and it's a positive value, so that tells me that it's 190 newtons forward. How many people got that? Good, good. For a first question, that's good. Let's take a look at question 2. It says in a tractor pull, 4 tractors are connected by strong chains to a heavy load. The load is initially at rest. Tractors A and B pull with 5,000 and 4,000. C and D pull with 4,500 and 3,500 in the opposite direction. The magnitude of the force of friction is 1,000 newtons. Let's find the net force acting on this tractor here. Here's the tractor. There's a force of 5,000 newtons. We'll call it FA. 5,000 newtons forward. We also have a force of 4,000 newtons forward. We'll call that FB. We have C that's 4,500 newtons backwards. Uh, 3,500 newtons backwards. We'll call that FD. And we have a force of friction of 1,000 newtons backwards. Kind of ran out of space here to draw the force of friction, but like I said before, it doesn't really matter where we draw it, as long as we've got it drawn in the right direction. We'll call this FF, 1,000 newtons. Now, those aren't perfectly to scale. That's okay. It doesn't have to be perfect. Just do your best to draw it to scale. Now, there are 2 other forces acting here. What are they? They're not going to matter, but they're there. Right, gravity and the normal force. But they're going to end up canceling each other out, just like they have in all the questions we've done so far. All right, let's get the net force here. the net force is equal to Fc plus Ff plus Fd plus Fa plus Fb. There's a lot of forces there. It looks kind of complicated here. Fc is neg 4,500 plus neg 1,000 plus negative 3,500 plus positive 5,000 plus positive 4,000. We add those up, what do we get? We add them up, we get 0. What's the net force acting on this tractor? 0 newtons. If an object is at rest and there's 0 net force acting on that object, what's going to happen to it? It's not going to move. So the answer to the second question, if the load is initially at rest, will it start moving? The answer is no. An object at rest will stay at rest forever until acted upon, not by a force, until acted upon by an unbalanced force. And these forces all balanced, so this tractor is going to stay where it was. Fraser? Okay, good question. Why is the friction force to the left there? Okay. How did we know that that was to the left? That's a good question, and I kind of skipped over that faster than I should have. That's a very good question. Okay. We know that friction acts, but we weren't told which way it acts. So how did I know to draw it to the left and make the net force 0? Anybody want to take a stab at that? Hayden? Good. If you have a force of 9,000 newtons to the right, and you have a force of 8,000 newtons to the left, if it's going to move to the right. So you have to oppose motion to the right. Well, if you're opposing motion to the right, which way are you acting? To the left there, right, Fraser? Yeah. That make sense? Yeah. If it was going to move, it's going to move to the right. It doesn't, but you have to oppose rightward. I don't even know if that's a word. Is rightward motion a word? Motion to the right. You have to oppose motion to the right. So the friction is going to be to the left. Good? Let's see if we can get this question done in the next minute here, okay? 2 athletes on a team A and B are practicing to compete in a canoe race. A has a mass of 70 kilograms, B is 75. The canoe is 20 kilograms. Athlete A exerts a force of 400, B 420, and there's water resistance of 380. What's the acceleration? Okay, real quickly here, I don't care how many guys are in this canoe. I don't care that we have a canoe. I care that the total mass of this is going to be 70 plus 75 is 145, 165 kilograms. That's what I care about. I care that there's a force to the right. We'll call it F1 of 400 newtons. I care that there's another force to the right. We'll call it F2 of 420 newtons. And I care that there's a force of water resistance to the left. We'll call it FW of 380 newtons. Now, there is gravity acting on this. Hold on one second, guys. We're almost done. There is gravity acting on this. There is a normal force. They cancel. The net force, just like it was before, is equal to the sum of the forces. That's Fw plus F1 plus F2. We don't worry about gravity and the normal force because they've canceled. Now, in this question, we have to go to that next step. M times A, Fraser, write this down, is equal to Fw plus F1 plus F2. Now we plug in the mass. The mass is 165 times A is equal to negative 380 plus positive 400, because this is to the right, plus positive 420. We get 165A is equal to, what is that, 820 minus 380 is going to give me 440. A is equal to 440 over 165, whatever that is, 2 point, anybody have that? 2 point something meters per second squared? 440 divided by 165. 2.66, which we're going to actually round to 2.6 meters per second squared. So a little bit more to this question than the last question, but not that much, just plugging in M times A. Your homework for the weekend, for the big, long weekend, are the practice problems on page 150. Problems number 1 and 2 on page 150. Okay? Have a good weekend, everyone, and we'll see everyone bright and early on Wednesday morning.